Well, thank you everyone for coming. This is our June club meeting, and as I mentioned earlier, we do have monthly club meetings here at the library once a month. Um, this is our typical agenda where we'll do some welcome remarks. We'll have Sarah Treadwell as our presenter for today. We'll open it up for open discussion, talk about upcoming events, and something that I don't have on the agenda. You've come to a very special meeting where you're going to have the ability to shape next club's meeting. And I'll speak more about that later. We'll do very quick conditions overview, but really we'll try to get outside once we're done with all that to see if we have a clear sky and enjoy using some telescopes that we have. So for anyone who does not know, my name is Isaac Osores. I'm an East Brunswick resident and have been for the last 12 plus years now. I am also a NASA Solar System Ambassador volunteer, but also very proud to be the president of the club at this present time. And we like to include our mission statement so that everyone knows with regards to the club, you don't need to be an expert in astronomy, have used a telescope before. In fact, some folks that have looked through the telescope for the very first time have done it through our club, which makes us very, very happy. Thank you. One other thing that I'll mention here, I won't read the whole mission statement, but we do invite folks to bring their telescopes with them if they would like to our club meetings. Especially if you're having trouble with them, we'll do our best to help you, get you set up, but we do have our own for you to look through as long as the conditions are good. Perfect. So with that said, I'd like to introduce Sarah Treadwell. As you may have seen on the poster and the Instagram and Facebook post, she does go by Space K Sarah online. She is a professional space communicator with a focus on astrobiology and a passion for following science wherever it leads. She holds a Master of Science in Communications from the University of Wisconsin, Whitewater, and is currently a PhD candidate in communications at the University of North Dakota. She also serves as a research science affiliate in the Science Communication and Education track with the Blue Marble Space Institute of Science. So with that said, let's welcome Sarah.
Thank you. You kind of did a good introduction for me that I had built into my presentation. But my name is Sarah. I go by Space K Sarah. I am an astrobiology science communicator, and my work focuses on connecting ocean research to space research. And I have found in my professional experience and in my personal experience, a lot of people don't think that those two things connect. But something I try to always remind everyone is that we are on planet Earth, which is a part of space, and our oceans are a part of space. So I don't have to actually give too much of the introduction that I built into here. Yes, I'm Sarah. I'm a PhD candidate, and actually this talk is going to be a part of my PhD research. So at the end, I'm going to beg for you to scan a QR code to take a survey on this presentation. Basically what I do in my PhD work is I am a communications professional that's looking at the most effective forms of communicating science. And so I have to kind of compare like flat screen presentations to doing presentations in a dome. So this is a flat screen presentation that I would love for you to participate in as part of my research. Yep, kind of everything here is covered. I'm also a solar system ambassador, and I'm super, super lucky to have had the last few years my work supported by really cool programs like the United States Science Support Program. I've won 2 NASA scope grants to support my planetarium work, and I also have had a couple of projects supported by the International Ocean Discovery Program. So as a professional science communicator, my work really did start a lot with space science. So I've participated in analog astronaut experiences. I frequently go on CNN to talk particularly about private space industry news. I got to go to ACEAP, the Astronomy in Chile Ambassadors Program. I actually went with Kat, who I know did a talk here with you guys. So she was in my cohort. So I do a lot in space science. And on a personal note, I also am really into very adventurous and extreme kind of activities. I scuba dive I've been to Everest Base Camp and went to Patagonia about a year ago. And I think the reason that I'm sharing all this with you is because, again, it's sort of like, how the heck did you end up on this? And some of it is just my extreme taste for adventure. But this ship that you see here, this is called the JOIDES Resolution. It was, unfortunately, got decommissioned and destroyed a few months ago, actually. Um, it was a ocean core drilling research ship that would go all around the world for various different types of expeditions. Sometimes it would be for like volcano research or a lot of geology, obviously, because it's a core drilling research ship. I got contracted to sail on this ship because of my interest in astrobiology. And so I've made this talk into two different parts. So the first part is I'm going to teach you about a lot of science, and then I'm going to share with you in the second part the experience of being on this ship and why it's so important and relevant to astrobiology science. I wanted to start this talk though with one quick kind of like thing that I find really funny. So kind of akin to space science and NASA patches, ocean research also loves their patches and their logos and their emblems. So every expedition would get their own patch and their own kind of little nods of what it was dedicated to in the patch. And you'll learn more about what all this means kind of through the talk. But one of the things that was really funny when the scientists wrote the proposal, the main point, the entire main point of our expedition originally was to go to, you see on the side here, it says U1309D. We were supposed to go to this hole that we were going to go core drill, the deepest hole that had ever been dug. And when we got to this hole, we sent the drill pipe down and immediately got stuck. And we got stuck so bad that we ended up having to blow the pipe loose. And then like all that pipe and the drill bit were in the hole in the ocean floor. So that hole was completely defunct. We did literally nothing with it. And so I like to tell people it's sort of like getting your boyfriend or your girlfriend's name tattooed on you. Don't do this, because now that number and that name of that hole is on this patch forever, and we didn't do anything with it. And we had a lot of fun with memes on my expedition. So we had a lot of fun making fun of this too, that the one hole that we were supposed to go to was not really not something we did with. And this one, 1601, you'll learn more about, is what we ended up doing quite a lot with. So and I added a lot of humor into this talk, so I hope you guys are okay. It's always kind of weird to talk to just a screen and not like know if people are chuckling or smiling or anything like that. Um, so here's your science crash course on astrobiology. I realize you are an astronomy group, but astrobiology to me is very interconnected in so many disciplines, and I think it's just a really cool science in general. This is the very sterile definition of astrobiology. But what I like to tell people, at least in my line of communication and work in astrobiology, I like to say that astrobiology is the search for, not the search, but the search for life in really extreme places for us to understand how we might be able to find it in the solar system. So as I mentioned, I'm really into extreme kind of adventures. And so that's why I think I was very drawn to astrobiology, because it requires you to have to go to very remote places on Earth to do research to find out how life exists in those places. This isn't to say that that is all of astrobiology. There is like broader, bigger philosophical kind of things to astrobiology. If you're familiar with this equation, this is called the Drake equation. And the Drake equation is somewhat of a thought experiment based on the known amount of different galaxies and potential planets around certain stars, how many civilizations, intelligent civilizations, might we be able to find in the universe? When people plug in the numbers for this, it's either like zero or like millions and millions. So this isn't, hard science, but it's definitely part of that big astrobiology kind of concept of, are we alone and how did we get here? So there's definitely more to astrobiology than just what I am very interested in. There's a whole big range of questions about aliens. And as I'm sure you all maybe have been aware, there's a lot of chatter about, aliens visiting us. And I cannot speak to this. So, if you want to know my thoughts about whether aliens have visited us and this is real, I can talk to you privately, but that is not what this talk is going to address. My talk is going to talk about life as we know it. And the life that we look for in astrobiology, in the work that I do and communicate in, is life in these extreme places where we find extremophiles. So these are actually, this is not a super scientific image. These are multicellular, but single cell organisms, we find them anywhere we find water, we find life on Earth. And we find it now in places that we would have never imagined. We've discovered that there are organisms that can basically make antifreeze in their blood systems, and they can live in the Antarctic, under the ice. So when we think of life and how it can exist, it constantly is pushing our understanding and our limits of how life exists. So when we think about life normally, we think about life as we know it, especially, here up on land, very mutual in how we all need each other. So we have, the plants that need light from the sun, our sun, to photosynthesize. And then it has that waste product of oxygen, which we take in, and we need the oxygen to break down food in our own systems to create our own energy. And then our waste product is the carbon dioxide, which the plants need for their photosynthesis process. So it's very, very mutual that we need each other. And this is how life has existed. And that was our understanding very solidly until one of my very favorite research vessels, a little sub named the Alvin. This isn't the Alvin from 1979, but the Alvin in 1979 made a very unexpected discovery. And this was the discovery of the very first black smoker hydrothermal vents. So for obvious reasons, this is called a black smoker because it looks like it's spewing out black smoke. However, this is not black smoke. That is melted rock. And that melted rock goes up, and then these towers are actually formed by that melted rock coming back down and rehardening. And it's incredibly hot, about 700 degrees Fahrenheit. Scientists were pretty sure they knew that they were going to be finding something like this at some point, but ocean research is incredibly difficult. I'm sure in astronomy you have heard we know more about the surface of the moon and Mars than we do about our own ocean floor. That is true for a lot of really complicated reasons. But it's, that's why we didn't find things until fairly recently. And so they weren't necessarily surprised that they found the black smoker, but what they were very surprised to find was that there was an entire ecosystem of life surviving off of these vent fields. These are the most famous things that we discovered, which are these giant tube worms that are living on some of these vents. And what is happening here is that the tube worms have a bacteria inside them that actually eats that melted rock. That's how it survives. So that starts the whole system of the food chain. So that's what supports the tube worms, and then the tube worms support other living organisms. And this was huge. Like, this is still considered probably one of the most significant discoveries in modern science, because this is the first time, as opposed to, we eat the plants, or we eat the animals, or the plants eat the sunlight. There's something eating literally chemicals. So we call it chemosynthesis. It's a totally different way of something to survive. And that just pushed the envelope even further into, holy cow, like, what are the limits of life and where can we find it? Because life seems to always find a way. So when we think about where these vents form, So this is a textbook image of what you are probably familiar with of how the system of the Earth works. We have the inner core, the outer core, we have this big layer that we call the mantle, and a very, very, very thin layer that is the crust of the Earth. If the Earth was the size of a grape, the crust would be about the equivalent of the skin of the grape on the Earth. That's how much there is on the inside of the Earth versus that crust, that outer layer. With that said, though, if you were anywhere standing on land, terra, earth, and trying to get down to the mantle, you cannot. It is too far down. We cannot get equipment to dig that deep. It gets too hot. The mantle is very, very hot. It's kind of a very dynamic layer where there's things melting and cooling and falling back down, and it's constantly moving and shifting. And that's why this image is also very scientifically inaccurate, because we're used to seeing the Earth kind of cut in half like this and you see these perfect spheres, but that's actually not how, especially the mantle works. So I'm going to switch to the next slide and show you how the mantle actually looks. And this is kind of the reason that these hydrothermal vent systems exist, because the mantle, so we have this sort of 3D kind of outside, that's the crust. And then you're going to see here now how the mantle blooms in different areas. And it's extraordinarily varied in how close it gets up to the crust versus how further down it stays. So that's why also these hydrothermal vents were hard to find, because it's not like the mantle is not uniform around the entire Earth. And so this is also why, just kind of a weird side, not weird, but a side fact, that there's different magnetic poles on the Earth, like, or not magnetic, gravity, I'm sorry. There's a little bit of different gravity around the Earth. It's because of the mantle and how it's interacting underneath the Earth's layer. So a huge reason that this is happening also is because of plate tectonic movement. Here's a nice map of some of the fault lines of the plates of the Earth. As we know, on the West Coast, they get a lot of earthquakes and then tsunamis because those plates are bumping into each other. But then on other parts of the Earth, the plates are actually not bumping into each other. They're actually pulling apart. So the Mid-Atlantic Ridge, that big line that's going right through the middle of the Atlantic Ocean, is actually pulling apart ultra, 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 ultra slowly. And what's happening is it's allowing the mantle to rise up in that part. And the highest part, one of the peak mountain points, is this part, the Atlantis Massif. And so that's where we're going to start talking about the Lost City. So the Lost City, and I'll talk to you more about that in just a second, is on this Atlantis Massif, and you don't really need to understand metric to, our United States weird measuring systems to understand the huge difference in elevation here. The Lost City is located at the top of this big mountain range where the mantle is pushing up. So this is called a bathymetry map, and it's showing you these different color scales, and that color gradient is showing depth. So the blue colors are where we're really deep in the ocean, and then the red colors is how it's rising up. And we're seeing a difference between 5,000 meters all the way up to 1,000 meters. So that's a huge elevation difference. And that makes these fault lines in the middle of the ocean really interesting for geological research, because we can actually reach mantle rock in these spots. It's not the Moho proper. I'm going to stop really quick and kind of explain that really super fast. But the Moho is this line that people have been looking for a really long time, where they want to find where the crust ends and the mantle begins. To my knowledge, there's just probably no technology that could ever get us to the Moho proper. This is the best we can do right now, which is find these points where the mantle is reaching up. So it is mantle rock. It's just not that line proper. Scientists get really picky about a lot of things, which brings me to my next slide. We are having a major nerd alert moment in our learning of science. And you guys are really lucky, because man, you think that like astronomers and space science people are nerds? No, no. No, get around geologists and rock people. This is an actual picture from a meeting I went to with some of the people I sailed with on my expedition. And let me tell you, sometimes I am fighting for my life when I'm looking at these. It's just, whew, it's heavy. It's super heavy. I call them the rock nerds, and I say it to their face. So we're going to be less of rock nerds in this presentation, and here are the important, well, really one important rock I need you to understand in the story of this vent field. That's really important for you to know why it's also important for space research. The deeper you go into the crusts and then down to the mantle, the darker you're going to see these rocks change because we are getting heavier metals pulled down. And the one that's really important to look at, I don't know if you can see my pointer or not, is this peridotite at the end. That one is the mantle rock, and that one is important. And the reason it is important is because, and you're going to see a name change here that is similar. It is because of a mineral called olivine. And you can see peridot is the gem quality of olivine. So you can see the matching and the names there. And olivine is a super common mineral. And it's a super common, especially in mantle rock. And we see it just literally everywhere. It's just olivine is everywhere. And why is that important? Well, this is very heavy chemistry now. We're going super nerd. When you have this mantle layer, and that's what you're seeing, this gray, and then you have the ocean above it, there are tons of cracks and pores and crevices that are going down into that rock. And scientists actually think that there might be 1 to 4 the amount of water on the surface of the Earth, like cycling through the mantle right now. And when it does that, the olivine has a very strong reaction to the ocean water. And it goes through a process we call serpentinization. This is very complicated. It's like a lot of chemical formulas and a lot of different things happen. And there's a lot of byproducts that happen from a serpentinization reaction. But we're just going to kind of hone in on a couple key things. The water has a serpentinized reaction, and it will start building up this crusty material that will start pushing up off the ocean floor. And as that material comes out, it also is spontaneously producing hydrocarbons, excuse me, like methane. And in particular, this one that I have circled, this HCOOH, that one's super important. It is basically what they call the Swiss Army knife of molecules. It's a really versatile chemical building block that a lot of scientists believe is the building block in abiogenesis. So the concept of if there's the right kind of chemical soup and the right amount of energy, can chemistry turn into biology? And we have been able to actually manipulate this formic acid in a lab. And when it reacts to other things, it produces one of the 4 thymine. It produces thymine, which is one of the 4 DNA building blocks. So this is really, 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 really interesting. And foreshadowing here, again, olivine is everywhere. And when we get meteors coming down to Earth, we find olivine all over inside them. This one is for, I don't know if my boyfriend is watching right now, but I don't know how to put this, but olivine is kind of a pretty big deal. So going back to my map here of the Atlantis Massif. So in 2000, a team of geologists, they're surveying this southern ridge. They are on a ship and they have a camera that they're literally like moving it up and down to just survey this wall. And there's a camera that looks forward, and there's a camera that looks to the left, and a camera that looks to the right. And there's 3 people that monitor these cameras. And as they're moving along, someone out of the right camera sees these like ghostly green spires. And they all kind of freak out. So I have been working on a book project for the last couple of years, actually interviewing every single person on this original discovery team and getting their stories about discovering this. And I also have access to all of the communication logs. And so when they see these, they're super confused because they know that there's hydrothermal vents. They're in a spot where the mantle's rising up. It makes sense. This is, something that can happen in this area. But these don't look like black smokers. They're not smoking. And they also they're huge. And so they can't figure out what they are. And in the logs, they're like, well, maybe they're, like extinct, like dead black smoker vents. So they realized, though, that this is something unique, something really interesting. We need to check it out. And they had the Alvin on board with them. So they take the Alvin down to go see it. And every single person I have spoken to says the same thing, that they see the most magical and glorious thing they have ever seen. It looks like a shimmery underwater waterfall. So this is there was a follow-up cruise. So this is video from the follow-up cruise. But as you can see, there is this shimmering. And what that actually is heat coming off of these green spires. So these green spires, if you remember, I said that the salt water goes into the mantle and it builds up this serpentinite and that kind of pushes up to the surface of the ocean floor of the crust. These are serpentinite towers that are bigger than we've ever seen ever. It just blew everyone away. And not only are they like these giant towers that are serpentinite, so there's depleted serpentinite, meaning it did as many of the chemical reactions as it can do, and it's done. A lot of it was still very active. It's a very active serpentinizing hydrothermal field. So when they took some fluid samples of it, they found that the temperature, so this is a temperature monitor, is around like 150 degrees Fahrenheit. So that's a huge difference between the 700 degrees of the black smokers. And while there aren't like those giant tube worms that live here, which kind of makes sense because there's no black smoke coming out of these vents are like teeming with bacteria and little like molecules of, not molecules, I'm sorry, little single cell organisms. And like, there's so much life all over these vents because they're not as hot as the black smokers. So this is a nice, cozy place for life to take a foothold. And if you remember, I said that these are also, as a byproduct, spontaneously producing these hydrocarbons that they feel are very critical to abiogenesis. So going back to my foreshadowing, we know that there is a ton of olivine in space rocks everywhere. So also in the 1970s, we had, for the very first time, a spacecraft that is very, 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 very near and dear to my heart, fly by Jupiter. This is Voyager. And it flew by, for the first time, one of Jupiter's Galilean moons. And this is the actual image of Voyager 1's first picture of Europa. And if you're familiar with Jupiter, Jupiter has, this huge gravitational pull. So it's sucking in, lots of asteroids. It has the asteroid belts around it. And what scientists were expecting when they got these closer up pictures of Europa was to see a moon that had a lot of impact craters, because it would make sense. It's by this giant planet that's sucking in all these asteroids, but it was actually really smooth and it had all these big cracks. And that was just super intriguing and indicative that there's got to be some sort of movement that's changing the surface of this planet. And so a lot of research went into this, obviously, because this was super intriguing. And they realized that this planet is covered in a thick, or not planet, moon, I'm sorry. This moon is covered in a thick layer of ice, and that there is some indication that it might have water underneath it. And so much water that it might be even more than we have on Earth. And more telescope observations have seen that not only is our Jupiter's moon in this state where it has this thick layer of ice and we see water pluming out of it. So when Jupiter gets close to Europa, the gravitational pull pulls so hard, it actually like pulls water out of it. that one of Saturn's moons also has the same thing. And scientists also realized from different magnetic measurings that there's definitely rocky cores to these icy moons. So it stands to reason, because we know olivine is so prevalent in asteroids and rocky bodies, that there are the right conditions to also have vent fields. And so in this image, you're seeing an artist's rendition, I can talk, rendering, there we go, of Europa and a potential white smoker system. So they call the Lost City a white smoker, which is kind of a misnomer because it's not smoking like the black smokers, but still, they have this kind of model showing like, well, maybe if there's a rocky core and there's a water rock reaction happening, maybe there are also Lost City-esque type vents there. And because we think that the Lost City might be an analog to how life got started on Earth because of those hydrocarbons being produced there, we're not sure, but maybe, what could be happening out there? And so NASA's taken the first steps into exploring that by sending the Clipper mission to Europa. It's on its way there right now. And Clipper is scheduled to reach Europa by 2030. And it is equipped with a ton of tools to look at the thickness of the ice, the cracks in the ice. It also has a tool that is going to try to catch some of that ejecta, the water and the rocks that they see pluming out through those cracks. There's no guarantees that it'll be close to it and the timing will be right and it'll actually be able to catch anything. But if the conditions indicate that there could be like vent fields like we have, like the Lost City on Europa, then it will send, NASA will send follow-up missions to these icy moons. I put this in, but I don't know what the status is on the development of this robot yet, but they're actually working at JPL to make like a snake robot to maybe crawl down into those ice cracks to then go further down to actually see if we can find any life. So, Sarah, how does this all connect to you sailing on an ocean research ship? Well, I was very, very fortunate to get to sail on this ship. We went out to the Lost City Hydrothermal Field area for 2 months. And I was contracted to be the onboard science communicator. And that was just the greatest job I could have ever asked for ever, because we primarily would do ship-to-shore broadcasts where we would interact with students of all ages and give them tours of the ship. So we could we had kind of free roam around the whole ship to show what the scientists were doing. We got to interact with the media. We got to just do quite a lot. And to give myself a slight talking break, I'm actually going to share with you now a video that I filmed everything on board for the Al Jazeera network. And then I will continue blabbing your ears off. So here we go.
Welcome aboard the Resolution. It's a 45-year-old oil drilling ship, but it's sailed most of its life as a science vessel. Its crew navigated to soft spots on the Earth's crust where rocks that should be hidden deep out of reach are pushed up by the movement of the planet's surface. In the middle of the Atlantic Ocean lies a mountain the size of Mont Blanc. There's no place closer to the Earth's mantle, the mysterious layer below the crust. It's called the Atlantic Massif, the Lost City. The scientists on board are studying these places where life may have begun.
But here, what's happened is we've had this faulting close to the mid-ocean ridge, which is kind of pulled like this. If you imagine my fingers of the mantle, they'll be down there, but they get pulled out like this until they're on the surface. And we see the mantle and the lower crust. The only way we can get to these by direct drilling is where there's a fault, because these rocks do not form on the seafloor.
They find a borehole that was drilled years ago. Using tools that can operate at high temperatures without electronics, they drill and scoop up samples along the way. They pull out the core, lift it to the surface in long plastic tubes, and remove the chunks one by one. Then the science begins. They want to capture every detail from the millions of years of history that are embedded in each piece. So it's sliced, loaded onto conveyor belts, and photographed.
So with a crusher split, we can see the inside of the rocks, and we look for a couple of major things. The first is what rock types we see. So we look for variations in the minerals that we see, variations in the rock type.
Because it's here in the alchemy of the early ocean where chemistry may have transformed into biology. When the greenish mineral olivine contacts seawater, it burns in a chemical reaction, creating new minerals and releasing gases through a process called serpentinization. Those gases, like hydrogen and methane, may have been fuel for the earliest forms of life. And understanding these reactions will give clues to so-called exobiologists who are looking for similar conditions under the icy oceans of the moons of Jupiter and Saturn.
There's people who are looking at this question of where that boundary is by looking at how life lives right now and trying to figure out what's common across all living domains. And so what those earliest forms of life might have looked like.
The resolution is likely retiring. Its annual US government fund of $50 million is coming to an end. The samples it digs up will be stored in vaults for study in the years ahead. Colin Baker, Al Jazeera.
Close my chat here so I can see my own screen. Yeah, that kind of just recapped again everything I just shared with you previously, kind of science heavy. But essentially, by understanding our ocean and our core of our Earth and our mantle and how our whole planet works and the limits of life, helps us understand how to create and design missions to go to places like Europa. Because other than quick flybys, we don't really know. I mean, we can do a lot of observation science and, measure different things to make very good speculations. But I'm truly, truly, truly excited to have Clipper be getting there. And I'm so relieved that it launched before. There's a lot of science missions right now that are kind of waffly on the chopping block for NASA. I'm so excited for what we might get and find out when we get to Clipper. And my expedition in particular is going to be extremely useful to Clipper when it arrives because, as Colin in the video explained, we were pulling up these core samples from the mantle rock. We first of all follow up on the drama of the story of, remember I said on the patch there was the number that didn't matter anymore. So we blew ourselves loose from the ocean floor, went to a different previously drilled hole, but there usually should be what we call re-entry cones when you go to these boreholes. They should be hopefully left behind, but not always. But usually you should put one in, because what happens is if you're core drilling down and then the ocean floor collapses on your pipe, that's how you get stuck. And sometimes the ship can get wiggled and you can break yourself loose, but in our case it didn't. And what happened with us also was that we had a very limited amount of charges. Some of them didn't work because I guess the way that explosives work nowadays, they actually become less effective over time, and they have been sitting on the ship for a while. So we were down to one charge, and we get to the next hole destination and we're like, okay, well, we need to drop a cone, because if we get stuck again, that's it, game over, no more science. And the pump that normally would slowly drop a cone down to the borehole, down the pipe, broke. So I have one more quick video here. What we had to do was literally cross our fingers and free fall drop the cone and kind of Hail Mary and hope that it would land like right and not like a little sideways. And that was the other hole that is kind of that joke that I showed you, the 1601. So this is the cone drop where this was really early on in the 2-month expedition too. And we were kind of just like, well, either this is gonna work or we're all going home very soon, much earlier than expected. Plane. So as you can tell, it worked. Well, the drop worked and it did land. And previously in areas on this Atlantis Massif near the Lost City, the ship had previously core drilled a record amount of mantle rock up to 97 meters with about a 40% recovery rate. So let me go back really quick to this one slide. This is what core samples look like when they come up. They're in these tubes. These are really nice core samples too, by the way. And they come up and the scientists will cut them in half, and then half will be used for research purposes that can be destroyed and the other half is preserved. And usually when the rocks come back up, they're usually very compacted and hot. And so they'll cool, and then some will like come out of the tube, and it's very uncommon to have a 100% recovery rate. So previously the ship had 98 meters with about a 40% recovery rate. We ended up pulling up 1,268 meters with almost a 100% recovery rate. This made my job on the ship exceptionally busy because every news outlet and then some were reaching out to us because this was huge. This was a geological triumph is an understatement, because that amount of meters is over 4,000 feet and it was continuous. We almost lost nothing. I had one person who was very knowledgeable about this when I gave a talk one time, and he was like, actually, it was like 98% recovery. And I was like, okay. I said almost. It was quite amazing. And again, it pulls into the allure of getting to the MOHO. Did we reach the MOHO? No, but did we get the most mantle rock that has ever been recovered? Yes. And why is that so important for Clipper? Because if Clipper is able to get these rock samples that come as it goes over Europa, what we pulled up will very much inform the science of understanding if there's life on Europa. One of the things the scientists did was a lot of the core samples was that they actually crushed them and then tried to see what they could bring back to life in the rock samples. And then we also had a special tool that went down in one of the boreholes, and it had shape memory alloys placed all throughout the tool. And so when certain temperatures were hit, it would spring open bottles for sampling. So we actually were able to sample like multiple points going down throughout the hole. And that paper is coming out soon, some of the findings of that. But we had our first paper, the very first thing that we had published was actually in the publication of Science for pulling up that much mantle rock. And I am always incredibly proud because my name is included too. And because I am dead last on the paper, they, have this like ... and Sarah Treadwell, like I'm on the preview page right there. So that was a huge moment for all of us. I mean, it was kind of an accident that I ended up on that expedition, and it turned out to be just utterly life and career changing. And one of the big things that happened to me as soon as I got home, I was like 3 days later, I was in a meeting with NASA Astrobiology, and they bring in this group called OpenSpace. And OpenSpace is funded by NASA and built out of the Natural History Museum in New York City. And they were showing us this software that you can use as a science communicator to share astrobiology science. And before I could even ask, they were like, but we don't have anything that goes under the water to like hydrothermal vents, because that's a big thing for astrobiology. And I was like, oh, that kind of stinks, because that's kind of what I just did. And then someone from the NASA Scope grant pops in my chat and she says, hey, you could work with OpenSpace and you could work with them to put the ocean elements in your expedition in OpenSpace and work in this planetarium software. So I always joke I'm an accidental planetarium person, but I truly am. I won the grant to do this. And after I won that grant, I realized, I am way in over my head and I don't know what I'm doing. And so I was able to borrow from a local group a portable planetarium dome system. And I started taking that out into my local community, and it took off like wildfire. I was still in development of my own show, so I was just doing like general planetarium show programs. And the community that I live in is, I'd say, comparable to like Detroit. So we don't have as many opportunities for students to go on field trips as some other school districts can. So for me to be able to bring the dome to them was huge and really, really important. And it truly has just changed the absolute course of my entire career and life. And I actually was able to win a second scope grant to buy my own portable planetarium dome system. And that system is actually currently en route to California because I do STEM camps with other NASA professionals now. And my dome show is now much more polished and much more finished. And so I connect this ocean research to the Clipper mission within the planetarium dome. But I mean, ultimately, it was an experience that I cannot. It was incredible. I have very high hopes and potential plans to return back out to the Lost City on a different ship because, as I said, this one was retired, and so this is sort of my little nod to thank you to the JOIDES Resolution for changing my life. Yeah, I could not have ever imagined such an amazing adventure to be a part of and to be able to build this story that shares with people all over how important the ocean and the ocean research is for us to understand Europa and Enceladus and how we're looking for life elsewhere. So it is definitely my pleasure to be able to come here and talk to you all about it. And like I said, I am doing research on this. You guys are definitely, you're one of my first, actually you are my first flat screen presentation guinea pigs here. So I have a QR code that if you would be so obliged to scan and give me some thoughts, I would greatly appreciate it. And then this same presentation, but just in a different kind of format in the dome, will be given to other people, other consenting 18-year-old adults, because if you've ever done research ever, you will know that IRBs are not fun. And I'm just measuring how much more powerful the medium of a dome is compared to other mediums, because I truly believe that the dome also is very, very special. So with that, I will leave this up and leave the room open now for questions.
Perfect. I think that we got a couple of questions already in the chat if we want to start there, maybe.
So yeah, okay, yes, I did keep a piece of one of the samples for myself. When the cores get split, they get cut in half, and a lot of chunks would fall into the sink. And one of the techs was like, "Hey, you could go grab some scoops out of the ocean or out of the sink before they just throw it back into the ocean." So I still have one of the biggest pieces from scooping those out before they got tossed back in the ocean. Lucas asks, any idea why we had a much higher success rate? Yes, there are a few factors why. One, we had really good weather. That's a huge factor, obviously. We also, we had, so a byproduct also of serpentinization reactions is asbestos, which was another kind of big problem we had on the ship. And that kind of softened the rock. So we think that some of it was highly, there was a lot of it in, some of it didn't have as much, but we think that that also kind of lent a bit to the success of it. But honestly, there was also like truly the techs were like, I've never seen anything like this. And I remember sitting on the ship and I was with a geologist, and normally, these rock nerds, they're so excited to get their rocks, but like everyone was getting burnt out. I even had to get trained to like work on some of the instrumentation to help process it because there was just so much coming up. Everyone was getting overwhelmed and really exhausted. What communication platforms what platforms do I use to, I do a lot of social media, platforms. I pretty much all of them. I tend to just grab my handle on every platform. Whether I use them as actively or not, depends. But I just kind of use whatever I feel like for social media and platforms to share my science. When I am contracted, like so for this expedition, when I'm contracted and there's certain, like I couldn't use TikTok when I was on the ship because we were part of, the lab was owned by Texas A&M and Texas A&M wasn't allowing TikTok to be on any of their servers and software.
Just to follow up on that one, do you have one that you prefer to use? One that you find maybe has a more engaging audience?
Kind of depends. That kind of goes into like communication science in general, right? There's a lot of science behind social media platforms of like, if you don't have people hooked by 3 seconds, they're going to scroll on. It kind of depends on the visuals, like that dropping of that cone. If I show that in the first 3 seconds, I might catch a lot more people because it's very visual and very high action, right? Versus if I just showed you some rocks in the first 3 seconds, I probably would get nobody. So it just really kind of depends on what I'm doing. I'm going to move on to the next question in the chat. Do you think serpentinization type vents are more origin of life compared to black smokers? I mean, I'm biased to the Lost City. I can't help it. I'm kind of in love with it. I know so much about it from working on this book and knowing everything about it. I do think black smokers have a lot of potential as well. I think the big debate that I see a lot with people is not necessarily which ocean thing. It's more like, was it was it life that came from somewhere else and it came down and started maybe in a shallow pool, or did it start at the bottom of the ocean? I'm very team bottom of the ocean, but I also, again, I have to say I am biased to the Lost City. Are there any uses for olivine or serpentinite? Are they just some pretty interesting rocks? I don't really think they're not really like, I think it's so common. They're not precious, right? I actually have some olivine somewhere, probably on my kitchen table, but, and how would you get in touch with me? Oh yeah, I suppose I was so busy, sharing my research QR code that I forgot to be like, follow me here. So you can find me on any social media platform as Space K Sarah. I also have a website, spaceksarah.com, and I have a contact page on there for that. I should stop sharing my page now. I'm sure you all scanned this.
Very cool. Does anyone here at the library have any questions for Sarah?
I'll start by saying that was a great presentation. You're a wonderful presenter. Clearly, you've been exposed to science in space and science at the bottom of the ocean. Which would you say is the more difficult environment to conduct research? Something like Challenger Deep, or out in space, say something past low Earth orbit?
I've put a lot of thought into this, and I really think ocean research is harder. It's not to say that space research is not hard either. I just think the pressure of the water is so unforgiving. Ocean Gate happened like 2 weeks after I got off of the ship, and so many people asked me about it. And it's not forgiving. You know what I mean? So I think ocean research is much harder than space research for that reason. And then also there's been a push to try to map all of the ocean floor by 2030. And I don't think that they're going to get that done because, when we're looking at the moon and we're looking at Mars and stuff like that, we can see things. We can actually visually see it and map it. We have satellites that can visually map it. The ocean, when you're sending sound waves down to do that bathymetry, the waves are slapping the boat up above, and those sound waves don't come back. So it's like painful to map the bottom of the ocean floor too, because it's slow and it's difficult. So I say ocean, but there's tons of challenges to space exploration as well.
I also like to say you did a fantastic job. It's actually on the subject of the life you find. It's clear you're looking for the origin of life, and you're looking at single-celled and multi-celled molecules and microorganisms. Does your research also include like the evolution of that, including multi-celled, like aquatic, like fish and such? And could it be possible that Europa and the rest could have this life if we do search for it, or even in some cases, life that can easily have a form of intelligence if this research does come into tuition of actually finding these microorganisms and seeing how they evolve?
Sure. I don't particularly study biology. I can just tell you what biologists tell me. The Lost City in particular has limited energy resources and food, so you're not going to find a lot of large life forms in that area because there isn't a food chain like the black smokers where there's a lot more energy sources for living organisms. I've heard from some science, I really have heard very mixed things from scientists about what could be found on Europa in terms of what energy is available to accommodate certain sizes of life. I've heard some people think that it could be there's enough there that we could maybe find like octopus size stuff. And then I've heard another scientists be like, no, there's no way there's enough energy coming out from Jupiter's, radiation and like that kind of stuff to sustain that. So I think that's what's just also like exciting and fascinating to me is that I don't know what we're going to find when we get to Clipper, but I know that whatever it is, it's not going to be what we expect.
I had a question regarding the tube worms and the
Mhm.
bacteria and their bacteria. Do we have any idea whether the bacteria is harmful to human life?
Oh, I don't know. That one I don't know. No, I I have no idea. Yeah,
It just
I'd have to
seems
look into that.
we're discovering a lot of things that we have no experience with in the past, and we were careful with that when we went to the moon to quarantine and so forth and so on. I'm just wondering what we do when we're down at the bottom of the ocean.
On the bottom of the ocean. Yeah, I honestly don't know like what research has, I'm without a doubt they, brought up the tube worms because that's how they know about the bacteria inside it. But I'm not entirely sure what the safety procedures are around dealing with that weird stuff down there. There's some weird stuff down there too.
This is Purusha. It's a fantastic work, and I'm very, very mind-boggling for me. Coming from oil exploration experience, well, I worked there in the oil field for 15 years. We take core samples, and that's about 15 meters, 10 meters, but what you got is something phenomenal, actually. And here we classify these things into formations like sandstone, limestone, clay. I'm talking about the crust part of it. What is
Yeah.
the composition of these core samples here?
What are they going to do with the core samples?
Yeah, what do you find? I mean, is it sandstone, granite, limestone kind of thing?
It's a lot of the peridotite and the gabbro rock.
Oh, okay. All
So
of it.
we were a hard rock core drilling sample. That's what we knew. We were going there for a hard rock. So sometimes if the ship was going on an expedition that knew it was going to sediment, we would have like micropaleontologists come with us. But because we knew we were, going for this hard rock, it was that we knew we were not going to be finding any fossils or anything, like that.
Yeah. Okay. And then there are no fossils, obviously. Then it's zero porosity. Porosity, that means where it can hold water or oil and all that kind of thing is there on the crust. But I don't think there is any porosity in the rocks, no. In the core
No.
samples, no.
No.
And I also remember in the USSR, long time ago, they drilled a hole some 12 kilometers deep.
Yes.
Right?
Yes.
They cored some parts
Creepy,
of it.
yes.
Yeah. I mean, I don't think they reached the mantle part of it.
No, they did not. No.
They did not, right? They closed it and all. They were scared to
Yeah,
open it now.
Yeah, they sealed it back up.
Yeah. Yeah, that's interesting, actually.
Yeah, that story kind of creeps me out. So what he's talking about is the Russians did try to reach the mantle from land, and they got pretty deep, but eventually it got so hot that their equipment melted, and so then they just sealed off the hole.
And also it's on land, not in the sea. They did that.
Yeah, they were trying on land. We just don't. I don't think it's possible on land.
Yeah. Okay. Thank you so much.
I'd like to thank you, Sarah, so very much for that very informative and interesting presentation. Let's give Sarah a hand.
Thank you.
Hopefully you can hear it since you can't see it.
I can't, but it's okay. Hopefully you're all super, super excited now for Clipper to get to Europa in 2030. I'm hoping to get back out to the ocean before that happens and hopefully have more cool things for my planetarium shows from that. So hoping it all times out great. And thank you for the accolades.
Awesome. Well, thank you so much. Take care.
You have fun observing if the weather is nice.
All right. So really quickly, we have a couple slides about upcoming events. Of course, we do have our next monthly club meeting in July. And if you were here during the May club meeting, you may have heard that we are looking to sort of revamp or rebrand our rapid fire presentations. This is something we did for the very first time last year in August. Was anyone here for that? The rapid fire? A couple. Great. So what that was an opportunity for you, our club attendees, to, instead of me being up here and blabbing for a little bit, having you present to the club. It's a very low pressure environment. We're very friendly. And the idea would be give you 5 to 8 minutes, and you can speak to an astronomy topic that speaks to you. Maybe about the eclipse experience that you may have had a couple years ago, a telescope experience that you got to see the rings of Saturn, whatever the case may be, just giving you an opportunity to speak to the club. Again, it doesn't have to be an hour. You don't have to have a Q&A if you don't like. But again, giving you an opportunity to do so. So we're doing this again, but we'd like to switch up the name a little bit. Before I move to the next slide, there is a QR code for the form that you would submit to show your interest. And it just asks some basic questions. What is the title of your presentation? A brief summary, a brief bio so we can introduce you properly. And we'll follow up from there. But please take a picture of the QR code or reach out to info@ebastro.org if you have questions. Here we like to share the upcoming events for the United Astronomy Clubs of New Jersey, which we are a part of. And they meet every Saturday at Jenny Jump State Forest. Here are a handful of the next couple of topics and speakers. Highly recommend you visiting. Has anyone gone to Jenny Jump? No? Highly recommend it. Certainly check the weather to make sure the sky will be clear, but they have a number of observatories that they welcome the public to look through. It's a great time. The presentations are interesting, so I highly recommend, if you haven't, to make the trip out there. Thank you for coming. We'll meet outside by the, what do we call it? Not the clock. Yeah, the courtyard area. You'll see us. You'll see the huge telescope. You can't miss it. But we'll meet there as long as the weather, the conditions are good. We'll see what we can see. All right. But thank you all for coming.